Let us start. Let us go through the different components of the refrigeration air conditioning system. And here we are going through, we have already discussed the compressor, condenser, and throttling valve, throttling devices. Now we like to continue and finish the evaporator system here. Now, what is the evaporator? It is an important device, you see, used in the low pressure side of the refrigeration system. Actually, this evaporator is doing the cooling post-cooling in case of refrigerator, that is the cooling chamber of the refrigerator itself, and for air condition, it is the cold chamber where we are the generally Hindu people will stay and get cold. This is the evaporator side. Actually, this is the evaporator. The cold liquid refrigerant from the expansion valve, it comes into the evaporator where it boils and changes into vapor. The function of the evaporator is to absorb heat from the surrounding location or medium, which is supposed to be cooled by means of the refrigerant. The temperature of the boiling refrigerant in the evaporator must always be less than the surrounding medium so that the heat flows to the refrigerant. So most important part is the temperature of the boiling refrigerant. It must be less than that of the surrounding medium so that the heat flows by convection to the refrigerant and get it cooled, get it evaporated. The evaporator becomes cold and thus remains cold due to the following two reasons. The temperature of the evaporator coil is low due to the low temperature of the refrigerant inside the coil, which makes the inside of the evaporator cold. The low temperature of the refrigerant remains unchanged because any heat it absorbs is converted to latent heat at boiling state. So the refrigerant is boiling and it requires a latent heat for its boiling, and it is absorbed the latent heat from its surroundings, that is absorbs the latent heat from the inside of the evaporator, which is housing its which is being housed by the which is being covered by this evaporator coil. Now, evaporator known as cooling coil, sometimes also chilling coil or freezing coil. Evaporator coil uses the refrigerant latent heat of evaporation to absorb heat from the medium being cold. The working of the evaporator. The working of an evaporator may be best understood by considering the simple refrigeration system as in the figure below. The corresponding pH diagram also shown here in the 0.45 of the figure represents the liquid, and liquid represent the expansion valve. What is shown here, this is the compressor where 0.1 is the inlet of the compressor, 0.2 is the outlet of the compressor. From compressor is compressing the the gaseous refrigerant, where it is compressed and sent to it condensed to a high pressure, and in gaseous state it is sent to the condenser, where it condensed to the liquid state and go to the 0.5, which is a receiver, which receives a liquid refrigerant, and from it is sent to the expansion devices. Where in the expansion devices, the pressure, high pressure from the compressor is reduces, and temperature is in liquid state. It is going to the liquid vapor mixture in the evaporator, where it is evaporated and becomes gaseous and goes back as a superheated vapor represent as in the compressor for being compressed. The 0.5 is this point is the represent the entry of liquid refrigerant in the expansion valve. Under proper property condition, liquid refrigerant is subcooled, means cooled below the saturation temperature, below its saturation temperature. But it's given here as 0.5 because it is saturation temperature for the liquid refrigeration at the 0.4. It is cooled 5 after the 0.5 and reached to the 0.5 where it is sent to the throttling devices where expanded from 5 to 4 and 5 to 6 at the 0.6 it becomes a mixture of gaseous and liquid refrigerant. The subcooling ensures that the refrigerant valve gets pure liquid refrigerant with no vapor present in the flow expansion valve. So this subcooling is required because it ensures the refrigerant becomes totally converted into liquid refrigerant and no vapor absorbed, no pressure is present to restrict the flow of refrigerant through the expansion valve. Because expansion valve can absorb and take the liquid refrigerant only, not the vaporized refrigerant. So it must be supplied with out and out 100% liquid refrigerant to make its expansion or its reduction of pressure possible. The liquid refrigerant at a low pressure enters the evaporator at 0.6. As in the above figure, it is entered to the evaporator at 0.6 here. Now, as the liquid refrigerant passes through the evaporator coil, it continually absorbs heat through the coil walls from the medium being cooled. It is continuously absorbs heat from the coil walls from the medium being cooled. So it is first it's getting absorbs heat from the coil wall, then from the medium being cooled. Then both of things it cools continuously. During this, the refrigerant continues to boil and evaporate. The refrigerant continues to boil and evaporate. Finally, at point 1 dash, all the liquid refrigerant has evaporated and only vapor refrigerant remains in the evaporator coil. Refrigerant continues to boil and continues to evaporate. Finally, at point 1, all liquid refrigerant has evaporated, means 1 dash. Here, it is up to this portion, it is a vaporized saturated vapor line. So up to this point, all the liquid, the vapor is supposed to be evaporated, and from 1 dash to 1, it has been superheated, it's heated more than saturated temperature. Finally, up to this point, continues to boil and evaporate. Next, at point 1 dash, all the liquid refrigerants are evaporated, only vapor refrigerant remains in the evaporator coil. The liquid refrigerant ability to convert absorbed heat to latent heat is not used up. So, first of all, we are subcooling the refrigerant from 4 to 5 to make it totally converted into liquid, thus exerting or exerting all the latent heat of liquidification or all the latent heat of liquefaction or freezing from air to from the refrigerant to air, and thus totally 100% liquid refrigerant is available for the expansion device to expand. At the point C, it is the expansion device expand and reduces the heat in the evaporator, when it is partially liquid and partially vapor state, and it's coated converting to vapor state by absorbing the latent heat from its wall of the tubes, wall of the refrigerant coil, as well as from the inside of the refrigerator, and then it's converting into by absorbing and cooling the inside of the refrigerator by absorbing the heat from the coil, and then goes back up to the point 1. It is reached the saturation point, and it is went up to the point 1 dash, it is totally got completely converted into gaseous refrigerant, and also it is heated up to a certain degree of superheat, so that it can feed directly to the compressor. This heat absorption causes an increase in the sensible heat or temperature of the vapor refrigerant or temperature. The vapor refrigerant temperature continues to rise until the vapor heats the evaporator to the suction line at point 1. This point, the temperature of the vapor is above the saturation temperature and vapor represented is superheated. So at this point to 1 to 1 dash, it is not only absorbing the latent heat which is supposed to be required for converting liquid to gaseous state, but it is sensible temperature also raised up to the point up to the point 1 dash, up to the point 1. Now this above figure shows the valuation representation temperature or sensible heat here, what we show here. The refrigerator heat content from 6 to 1 dash evaporation takes place, 1 to 1 dash superheated vapor. It is the refrigerant heat content. And refrigeration temperature sensible heat is raised from 6 to 1 dash. So what is going to, it is telling us the variation of refrigerant temperature sensible heat and the refrigerant heat content and enthalpy within the refrigeration. It is the heat content within the evaporator, heat content or heat enthalpy within the evaporator, and the variation of refrigerant temperature sensible heat. We see that the temperature of the refrigerant is constant during evaporation of the liquid refrigerant from 0.6 to 1 dash, and the enthalpy increases steadily. The temperature of the refrigerant is constant during evaporation of the liquid refrigerant from 6 to 1 dash, and the enthalpy increases steadily. It shows that the latent heat is absorbed by the evaporative liquid with no change in temperature. Both the temperature and the enthalpy of the refrigerant increases from 0.1 dash to 1. At point 1, all liquids are evaporated. 1 dash is the increase in sensible heat in the vapor refrigerant. So up to the there was no at 1 dash, there's no temperature rise of the refrigerant takes place. It is only absorbing the latent heat, and from 1 dash, it reaches up to 1 dash, it absorbs certain sensible heat, so the temperature raised from 1 dash to 1 dash. The heat absorbed by the refrigerant, why it is evaporated, accounts for most of the cooling accomplished by the evaporant. In other words, the cooling is due to the evaporation of the refrigerant rather than to increase the refrigerant sensible heat. Increase the refrigerant sensible heat. The capacity of an evaporator. The capacity of an evaporator is defined as the amount of heat absorbed by it over a given period of time. Defined as the amount of heat absorbed by it over a given period of time. Means what is the amount of heat it is absorbing for a period. After this, but important is the period of time. Certain amount of time, how much it is absorbing. Heat absorbed by or heat transfer of the heat transfer by an accident. Purpose capacity of evaporator is given by Q is equal to U into A T2 minus T1. U into A, heat absorbed or heat transfer capacity of the evaporator is given as Q, U into A, T2 minus T1 into W, or U overall heat transfer coefficient in watt per square cubic meter in per degree rise and fall in temperature. In amount in watt in per square meter of area by per degree centigrade rise and fall in per degree centigrade rise and fall in temperature. That is the overall heat transfer coefficient. A is the area of the evaporator surface. So that this area matches with this meter T2, temperature of the medium to be cooled, or temperature outside the evaporator degree centigrade, and T1, saturation temperature of the refrigerant at evaporator pressure or temperature inside the evaporator in degree centigrade. So T1 temperature of the begier to be cooled, T2 temperature of the begier to be cooled, the temperature outside the evaporator, and saturation temperature of the refrigerant at evaporator pressure, which or temperature inside the evaporator. So temperature outside the evaporator minus temperature inside the evaporator. That is the amount of cooling we are supposed to cool. The outside temperature, we have to cool it to the inside temperature, the area of the cooling through which area of the evaporator surface, and the coefficient of heat transfer. Overall coefficient of heat transfer. It should be in watt or in joules per second. In watts or in the factor affecting the heat transfer capacity of the evaporator. Now, what is the factor affecting the heat transfer capacity of an evaporator? So there are many factors upon which the heat transfer capacity of the evaporator depends. But yet the following are important from the subject point of view. Say material. In order to have rapid transfer in an evaporator, the material used for the construction of the evaporator coil should be good conductor of heat. So material which is not affected by refrigerant must be selected, which is not affected by refrigerant. Since metals are best conductor of heat, therefore they are always used for evaporators. Iron and steel can be used with all common refrigerant. Brass and copper are used with all refrigerant except ammonia. Aluminum should not be used with ferrous. So there are certain combination that it should be metal and like iron, steel. Metal here, that is iron and steel. Sometimes brass and copper with certain resistance. And what's important part is metal should be material should be metal used should be good conductor of heat and not react with refrigerants. Next is the sample temperature difference. The temperature difference between the refrigerant with the evaporator and the product to be cooled plays an important role in the transfer capacity. That between the refrigerant and refrigerant with the evaporator and the product supposed to cool, what is the temperature between the product which we have to cool and what is the temperature of the evaporator? The following table shows the suggested temperature difference. The cooling temperature, the say cheese, egg, butter, it should be -2, 0 to -2. And refrigerant temperature should be -10. So their difference should be 8 degrees centigrade. So meats and poultry, frozen meats should be -20 to -15. The refrigerant should be less than that, should be around 30, 30, means at least 10. difference is 10. Vegetable and fruits, it should be +7, and that's sufficient. And if said should be -5 degrees centigrade. Difference should be 12. Cream and milk should be +3, and that is okay. It's -8, and it should be 11. And beer 4.5, and should be -7, 11.5. So the difference between this cooling temperature as well as the refrigerant temperature should not be around 10 to 11, 10 to 12 degrees centigrade. And the coolest refrigerant temperature should be the poultry or meats, which is supposed to be cooled to 20 to 50 degrees centigrade, -20 to -50 degrees centigrade. The too low temperature difference between, say, below 8 degrees may cause slim or certain products such as meat or poultry. On the other hand, too high a temperature difference causes dehydration. So temperature difference below 8 degrees may be cause sleep on certain products. On the other hand, too high temperature difference causes excessive dehydration. The degree of refrigerant. The velocity of refrigerant also affects the heat transfer capacity of an evaporator. Velocity of the refrigerant. It's also heat transfer capacity of evaporator. If the velocity of refrigerant flowing through the evaporator increases, the overall heat transfer coefficient also increases. But this increases velocity will cause greater pressure loss in the evaporator, and thus only the recommended velocities for different refrigerant, which gives high temperature heat transfer rate and allowable pressure loss, should be used. The velocity is so important now. The heat transfer capacity, the velocity is flowing through the evaporator increases, so overall heat transfer also increases. So heat transfer coefficient increases with velocity. Heat transfer coefficient increases with velocity. But this increased velocity will cause greater pressure loss in the evaporator. But pressure also reduces the evaporator, thus the only recommended velocity for different refrigerant which gives high transfer rates, allowable pressure should be used. Allowable pressure loss should be used. So there should be a pressure loss or associated pressure loss. High rise in velocity will be associated with pressure loss. In general, the thickness of the head should be high temperature heat transfer rate. So recommended velocities for different refrigerant with high dispersion rate with allowable pressure loss should be used. Next is the thickness of the evaporator coil wall. Thickness of the evaporator coil wall will also affect the heat transfer capacity of the evaporator. Thickness will affect the heat transfer capacity, evaporator coil wall. In case the thicker the wall, the slower the rate of heat transfer. Since evaporator coil is under pressure, therefore evaporator wall must be thick enough to withstand the effect of the pressure. It must be noted that the thickness only has a slight effect on the total heat capacity because of it evaporates that are usually made from highly conductive material. So what we do here, thickness should be affect the heat transfer coefficient. So thicker the wall, coefficient will be higher. Since the refrigerator coils are under pressure, therefore the evaporator wall must be thick enough to withstand the effect of that pressure. It may be noted that the thickness is only a slight effect on total heat transfer coefficient capacity, because the evaporators are usually made from highly conductive metal, but thickness have side effect. But what, because really they are made from highly conductive metal. Contact transfer, contact surface area. An important factor affecting the evaporator capacity is the contact surface area between the walls of the coil and medium being cooled. How much contact is there between the evaporator wall and medium of the cool? The amount of contact surface area depends basically on the physical size and shape of the evaporator coil. Depends on the physical size. Longer and bigger the shape of the evaporator coil, it will have bigger the amount of contact surface and bigger the amount of heat transfer. Just 1 second, please. Next is the heat transfer evaporators. This heat transfer evaporator has three resistance in its path. The resistance of the medium being cooled, it may be air, it may be water, brine, or any other fluid or weighted surface of cooling and humidified coil. or a weighted surface of cooling coil. The resistance of metallic wall of the tube liquid, resistance of cooling medium, refrigerant film which gets heat from solid metallic walls, resistance of cooling medium, the refrigerant film which gets heat from the solid metallic wall, the resistance of metallic wall, and resistance of the medium being cooled. These are all the three resistances in this path for cooling. Now, heat transfer during boiling. The mechanism of boiling is so complex that it's difficult to predict the heat transfer coefficient. Now, it is difficult to predict the heat transfer coefficient, but it is due to the factors such as latent heat affects surface tension, saturation temperature, nature of solid surface. It is due to the factors such as latent heat affects surface tension, saturation temperature, nature of solid surface. The boiling occurs in the following two ways: pool boiling as it occurs in flooded evaporator, and flow boiling or forced convection boiling as it occurs in direct expansion evaporators. Pool boiling as it occurs in flooded evaporators, and flow boiling or forced convection boiling as it occurs in direct expansion evaporators. When heat is added to a liquid from a submerged solid surface, the when heat is added to a liquid from a submerged solid surface, the boiling process is called pool boiling. A necessary condition for the occurrence of pool boiling is that the temperature of the heating surface exceeds the saturation temperature of the liquid. So boiling two boils. Pool boiling, it occurs in flooded refrigerators. Flow boiling or forced convection boiling as it occurs in direct expansion evaporator. Forced convection, flooded refrigerator, forced convection boiling in direct expansion evaporator. When the heat is added to a liquid from a submerged solid surface, the boiling process is called pool boiling. It is added to liquid from a submerged solid surface. Heat is added to a liquid from a submerged surface called pool boiling. The necessary condition for occurrence of pool boiling is that temperature of the heating surface exceeds the saturation temperature of the liquid. In this process, the vapor produces away from bubbles which grow, subsequent detach themselves from the surface, rising to the free surface due to Boyle's effects. On the other hand, the flow boiling or forced convection boiling occurs in a flowing stream, and the boiling surface may itself be a portion of the flow passage. This phenomenon is generally associated with two-phase flows through confined passages. The process of pool boiling is shown as below in the figure. The heat flux QA, this is given here, and is plotted against the excess temperature delta T, Tw1 is Ts in degree centigrade. The pool boiling experiments have been done so that the boiling process of liquid at the saturation temperature is the following three distinct regimes: internet, intersurface evaporation, nucleate boiling, and field boiling. What is intersurface evaporation? This occurs the free surface without the formation of bubbles. Free surface without the formation of bubbles, solid wall temperature, the wall Tw only few degrees above the saturation temperature of the boiling evaporative substance. Free surface occurs at free surface without formation of bubbles. Nucleate boiling. When the excessive temperature increases, vapor bubbles are formed. This bubbles rises above the metal surface but condenses below the reaching the liquid surface. Condenses before reaching the liquid surface. When the excessive temperature delta T is further increased, the bubbles rise and collapse to the free surface by limit surface tension. This process is called nucleate boiling. So what is that? Excess temperature increases delta T. The vapor bubbles are formed. These bubbles rise above the metal surface but condense below the reaching the liquid surface. When the excessive temperature further increases, bubbles rise and collapse through the free surface by limit surface tension. This process is called nucleate boiling. When the maximum heat plus is reached at a point A, the heating surface gets covered with proper vapor bubbles causing the film boiling process. The maximum heat plus is reached at a point A. Then all the heating surface get covered with vapor bubbles causing the film boiling process. The heat transfer is flattened evaporators is corresponding to second regime of nucleate boiling. So three types of boiling: evaporation, nucleate boiling, film boiling. Evaporation, the free surface without formation of bubbles occurs at frequent surface. When the excessive temperature bubbles are formed, these bubbles rise above the metal surface but condense below the reaching of liquid surface. When the maximum heat plus is reached at point A, the film boiling, all the boiling heating surface gets converted with vapor power, causing the film boiling process. The heat transfer in flattened evaporator is corresponding to second regime of nucleate. Next, what is the heat transfer coefficient? Experimental data for nucleate pool boiling are coordinated by Ransom as given below. CF TW minus TS divided by HFG, which is equal to CSF multiplied by Q divided by A divided by mu F multiplied by HFG square root of sigma G rho F minus rho G to the power minus 1/3 multiplied by C mu divided by K to the power F to G. CF, the specific heat of transfer saturated liquid, specific heat of saturated liquid. TW by TS, excessive temperature in Kelvin. HFG, enthalpy of variation in kg. HFG, enthalpy of variation. CSF, an empirical constant, is value 0.13 for combination of copper tube. Q by A, heat flask in watt per mix per meter, Q by A. Then mu F, viscosity of saturated liquid in kg per meter second. Sigma, surface tension of liquid vapor interface in Newton per meter. G, acceleration due to cavity in meter per second square. Rho F, density of saturated liquid in kg per cubic meter. Rho G, density of saturated vapor in kg per meter cube. The fluid side heat transfer coefficient. Now, fluid side heat transfer coefficient is given by this formula, Ck divided by T. V D into rho divided by mu to the power 0.8, Cp into mu divided by K to the power 0.4. HF, fluid side coefficient, fluid side heat transfer coefficient. C is a constant, K conductivity in watt per meter per Kelvin. T, inside diameter of the cube. V, velocity in meter per second. Rho, density of fluid. Mu, so viscosity is kg per meter second, and Cp is a specific heat at constant pressure in kilojoule per kg. So that's fluid side heat transfer coefficient, and another is for nucleate pool boiling. Following under some special cases of equation 1 is for liquid flowing through the evaporator shell, HF is a C into root over F. and mass flow rate of the liquid. The air flowing over field coil by forced convection, HF C into m to the power 0.4. For air flowing over cold pipe by natural convection, HF is 0.2 TA minus T ampere by T to the power half, 1 by quarter. TA drive of temperature of air and TA mean temperature of pipe surface. Next, let us go to what is the type of the evaporator. According to the type of the construction, there are 4 different types. Actually, 6 different types. Bare tube coil evaporator, thin tube, plate evaporator, shell tube evaporator, shell and coil evaporator, tube and tube evaporator. According to the matter in which the liquid vapor is feed, flooded, and dry expansion evaporator. According to the mode of axial convection evaporator and forced convection evaporator. According to operating condition, frosting evaporator, non-frosting evaporator, defrosting evaporator. We now go through the above mentioned evaporator details. Bare tube coil evaporator. Bare tube evaporator. The simplest evaporator is the bare tube coil evaporator, as in the figure, where the liquid mixture comes in through a valve, expansion valve here, then goes to the evaporator coil, then comes out to the suction to the compressor coil. So bare tube evaporator known as prime surface evaporator. The bare tube coil evaporator is known as prime surface evaporator because it's a simple construction. Bare tube is very easy to clean and defrost. A little consideration will show that this type of evaporator offers relatively liquid little surface contact area as compared to the other type of coils. The amount of surface area may be increased by simply extending the length of the tube, but there are disadvantages of excessive tube length. The effective length of the tube is limited by the capacity of expansion valve. If the tube is too long for the valve's capacity, the liquid refrigerant will tend to completely vaporize early in this process to the tube, thus leading to excessive superheat at the outlet. The long tube will also cause considerably greater pressure drop between the inlet and outlet of the evaporator. This results in a reduced suction time. So here, this is the simplest way of method to evaporator. It can be easier to clean, and the amount of surface area can be increased by simply extending the length. But there are advantages and disadvantages. The effective length of the tube is dictated by the capacity of expansion. If it's too long for the valve capacity, liquid will tend to completely vaporize early in the process. Long tubes also cause considerably greater pressure drop between the inlet and outlet. This results in reduced suction line pressure. The diameter of the tube in relation to the tube length may also be critical. If tube diameter is too large, the refrigerant velocity will be too slow. And the volume of refrigerant will be too great in relation to the surface area of the tube to allow complete evaporation. In this term, they allow with possible damage to compression that is sluggish. On the other hand, if the diameter is too small, the pressure drop due to friction will be too high and it results in loss of system efficiency. The amount where coil evaporator pairs should be used for any type of process. It uses, however, limited to applications where the box temperature are under 0 degree centigrade and in liquid cooling because the accumulation of ice or frost in the evaporator has less effect on the heat transfer on the equipped with fins, on those equipped with fins. The bare tube coil evaporator also excessively used in household refrigerator because they are easier to keep clean. Next comes the fin evaporator, as like under below. It is consists of a bare tube or coils over which the metal plates of fins are fastened. Here, this is the evaporator coil, and here upon which the fins are being fixed. The metal fins consist of thin sheets of metal having good thermal conductivity. The shape, size, or spacing of the fins can be adapted to provide best rate of heat transfer for a given application. Since fins are since the fins greatly increase the contact surface for heat transfer, therefore fin evaporator also called extended surface evaporator. The vapor refrigerant comes through the fins and vapor refrigerant comes in through plate and goes out. Fin evaporators are primarily designed for air conditioned applications where refrigerant temperatures above 0 degrees centigrade. But the rapid heat transfer of fin evaporator, it will defrost itself in the off cycle when the temperature of the coil is near 0 degrees centigrade. A fin coil will never be allowed to frost because the accumulation of frost between the fin reduces the capacity. The air conditioning coils, which operates at suction temperature which are high enough so that the frosting never stops or occurs, have fin spacing as small as 2 millimeter. The fin coils with most of the on one cycle and frost on the off cycle on the frost on the on cycle. A plate evaporator. A common type of evaporator shown in the 16 minutes here. This is a plate evaporator. In this evaporator, coils are either welded on one side of the plate or between two plates, which are welded together at the edges. The plate evaporator is generally used in household evaporators, home freezers, beverage coolers, ice cream cabinets, locker plants, etc. Shell and tube evaporator. In the shell and tube evaporator, the shell and tube evaporator, as in figure, is a smaller to a shell and tube condenser. It consists of a number of horizontal tubes enclosed in a cylindrical shell, and its inlet and outlet headers are perforated metal sheets which are connected to each end of the tube. So what is this? It's a shell and tube condenser like this. The liquids are coming in and chill liquids are coming out, and vapor refrigerant comes from the goes to the compressor, and liquid refrigerant comes from the expansion valve to the evaporator itself. That there are baffles for the valves for the proper circulation of the liquid refrigerant. So here the liquid wants to cool, it comes in and being circulated throughout the vapor refrigerant and is cooled by the vapor refrigerant as is absorbing heat for its evaporation from this liquid, and this heat liquid goes out through here after the proper circulation and from the vapor refrigerant. The inlet and outlet headers are perforated with metal sheet contacting each end of the tube. These evaporators generally used for chilled water or dry solution. When it is evaporated in a dry expansion evaporator, the refrigerant circulates through the tube and the liquid to be cooled fills the space around the tube within the shell. The dry expansion shell and bulb at the tube evaporator is used for refrigerating units of 2 to 250 TR capacity. When it is operated at a flat evaporator, the water or brine flows through the tubes and the refrigerant circulates around the tube. The liquid shell and tube evaporators are used for refrigerating units of say 10 to 5,000 practical capacity. So generally, what is given here, it is for make cool water or make cool blind solution. But it operated dry expansion evaporator, refrigerant circulates through the tube and the liquid to be cooled fill the space around the tube. The dry expansion shell and the tube expanders are used for refrigerating coil of 2 to 250 tons capacity. When it is operated at a flattened evaporator, the water or brine flows through the tube and the refrigerant circulates around the tube. The flattened shell and tube evaporators are used for refrigerating units of 10 to 5,000 tons capacity. Shell and tube coil evaporator in figures are generally dry expansion evaporator to chill water. Generally dry expansion evaporator to chill water. The cooling coil is a continuous tube that can be in the form of a single or double spiral. Right? The cooling is a continuous tube that can be formed a single or double spiral. The shell may be sealed or open. The sealed shells are usually found in the shell and coil evaporator used in the cool drinking water. Evaporators having flange shells are often used to chill water in secondary refrigeration system. Another type of tube and coil evaporator is shown. Both types of evaporators are used, but small capacity liquid cooling is required. It may be noted that the shell and coil evaporator is restricted to operate above 5 degrees centigrade in order to prevent the freezing problem. Tube in tube or double tube evaporator. Here, just a second. Tube in tube or evaporator as shown in the figure consists of one tube inside another tube. The liquid to be cooled flows through the inner tube while the primary refrigerant or secondary refrigerant circulates in the space between the two tubes. So refrigerants are coming in and circulating throughout it, and liquid to be cooled goes through that inside the tube. The tube in tube evaporator provides high heat transfer coefficient. However, they require force fed than shell and tube evaporator. This evaporator is generally used for wine cooling and petroleum industry for chilling in the oil. Flathead evaporator. In a flathead evaporator, as, as in the figure below, like this, a constant liquid refrigerant level is always maintained. A flat float control valve is used as an expansion device which maintains constant liquid level in the evaporator. The liquid refrigerant from the receiver passes through a low side float control valve and accumulator before entering the evaporator coil. The accumulator, also defined as a surge drum or surge tank, serves as a storage tank for the liquid refrigerant. It maintains a constant liquid level in the evaporator and also helps to separate the liquid refrigerant from vapor returned into the compressor. Due to the heat supplied to the process to be cooled, the liquid refrigerant in the evaporator coil vaporizes and thus the liquid level falls down. The accumulator supplies more liquid to the evaporator in order to keep the liquid refrigerant in the evaporator at proper level. Thus, in this way, the level of liquid refrigerant in the accumulator also falls down. Hence, the float within the float chamber based on the liquid refrigerant at the same level as that in the accumulator. Therefore, the float auto falls down and opens the float valve. Now, the liquid refrigerant from the receiver is admitted to the accumulator. As the liquid level in the accumulator rises to the constant level, the float valve also rises with it until the control level valve closes. Since the evaporator is almost completely fitted with liquid refrigerant, therefore, the vapor represented from the evaporator is not superheated but in saturated condition. In order to prevent liquid refrigerant to enter into the compressor, the accumulator is generally used within the evaporator, flathead evaporators. The liquid refrigerant trapped in that accumulator is recirculated to the evaporator. The evaporator coil is connected to the accumulator and the liquid flow from the accumulator to the evaporator coil is generated by gravity. The vapor formed by vaporizing the liquid in the evaporator being lighter, the riser up rises up and passes on to the top of the accumulator from where it is supplied to the suction side of the compressor. The